evaluated excess heat from the platinum electron. So have you some ideas to get some excess heat from platinum, like platinum?
Sorry, could you repeat more slowly?
You could answer to the first question first.
For first question, how big the error
Experimental error.
or experimental error or evaluation of excess heat? Error.
Ah, 100 milliwatts.
Milliwatt.
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 100.
So the 0.1 watt
Yes.
that you get from the platinum electrode.
Okay. So so this value are out of the error. We are quite sure that the excess is over the error, and in this experimental point, we were using a very low current density, and the power input was about 2 watts. In the first 10 watts of the calorimetry, we can observe an error less than 50 milliwatts. So we are quite sure of this.
Thank you.
And the second question.
That's all. I will ask you in another chance.
Oh, okay.
Yes.
There's a confusion. The platinum is the anode, not the cathode in that experiment. These are all experiments with palladium cathodes.
Yeah, all experiments are palladium cathodes.
Yes, that's important. Yes. So there are many questions. I must go to the next speaker. Who is going to be Professor Hamada. Who is going to talk about anomalous heat evolution of different implanted arena and electron combustion.
Mr. Chairman, ladies and gentlemen. I'm now talking about the normal heat evolution of heat. Oh, sorry.
Yes. That's right.
I'm now talking about the anomalous heat evolution of deuterium implanted aluminium, not palladium, on electron bombardment. In this report, I'd like to talk about the anomalous heat evolution which produces the melting of the aluminum surface. Investigations on possible mechanisms of this surface melting, namely on chemical reactions and other mechanisms based on the electron beam heating of aluminum. We conclude that the fundamental mechanism should be a nuclear reaction, though we can specify what kind of nuclear reaction is active. And this nuclear reaction must finish in less than 20 picoseconds in a very short time. And I talk about the experimental procedures of this experiment, since it's quite a little bit different from other experiments. It consists of 2 parts. First of all, it's implantation of D plus ions in the aluminum. The aluminum specimen was made of 49 purity aluminum, and it was shaped into a 10 disc. It means a transmission electron microscopic disc. And the energy of ions, implanted ions, and its ion species are 30 keV D2 plus. So it means 15 keV for every D1 plus. And ion current is less than 1 microampere through 3 millimeter diameter slit. And ion dose was near around 4 times 10 to 17 D1 plus per square centimeter, and temperature is room temperature. And next, the 10 of the implanted aluminum specimen was observed by electron microscope. And the electron microscope used was a Hitachi H700. And electron energy was 175 keV. And electron beam intensity was more than 1 times 10 to 19 electrons per square centimeter per second. It means actually in the course of the experiment, it was about 60 nanoampere per 3 micrometer square. And this is a very important point in this experiment. Usually, when electron microscope people do experiment, they first do defocus the electron beam and irradiate the specimen in a wide range and look for the part of the specimen to be studied, to be observed. And then after that, they focus the electron beam a little bit about this amount of electron density. And this melting was observed after the focusing of the electron beam. When we observe the specimen with a defocused electron beam, we can't observe such melting at all. So it means that this melting is not a result of the implantation, but it's an electron beam focusing effect. Secondary, experimental results and analysis. First of all, transmission electron microscope observation was done on 3 kinds of specimens. First of all, soon after the implantation, maybe in 20 minutes or so at room temperature, we observed this specimen in electron microscope. And secondly, after keeping the implanted specimen in liquid nitrogen for about 24 hours or more. And in these 2 cases, we could observe the melting of the surface. But after keeping the implanted specimen at room temperature, more than 24 hours or around 24 hours or more, we could not observe this melting, as I will mention later, at all. And also, when the specimen was implanted with a hydrogenized ion, we could never observe the melting. And the melting, which I'm saying frequently, is shown in this electron micrograph. This is the electron micrograph, and you can see the magnification of the photograph. And the top one, A, was taken after the implantation with hydrogen. And these are white, in a bright region, in bright regions contain the hydrogen molecules. Since the electron beam, dissipation of the electron energy is less through the hydrogen coagulation than through the aluminum matrix. So these hydrogen coagulation is observed as a bright images. And exactly the same experiment was done with deuterium implantation. And after, as I said before, just after the focusing of the electron beam, we observe such photograph. And you can see some speckled regions around here, and the main speckled region in this photograph. These regions this electron diffraction spot shows that in case of hydrogen implantation, everywhere in the specimen is single crystalline. And it's also single crystalline, even if the deuterium implanted case. When we take the diffraction around these regions, excluding the speckled regions, but including speckled regions, we observe these circular spotty rings. It reflects the presence of a polycrystalline part. So it means these regions, these speckled regions, changed from single crystalline to polycrystalline structure. And as far as I know, the transformation from single crystal to polycrystal in aluminum, in very pure aluminum, cannot be observed without melting, through melting. So I conclude that these speckled regions appeared because of the melting of the aluminum, which is never observed in hydrogen implanted case. And this is the perspective view of the implanted aluminum. I hope it is seen as three-dimensionally. These are some things here. Looks like a tunnel in the subsurface layer, and it is what I call the tunnel structure, and it is the same one. It illustrates these bright contrast region and contains much hydrogen molecules. And these hydrogen molecule tunnel structure is in about 90 nanometer from the depth. And the specimen, the bottom specimen, the deeper part of the specimen has roughly 1 order of magnitude thicker. And if we look the specimen, its cross perpendicular to the cross section, it must be like this. The aluminum specimen was made into a 10 disc, so it has about a 1 millimeter diameter and a very thin and small hole here in the central part, and very thin near the hole, and thicker in the we depart from the center. And the specimen, average thickness of the specimen is roughly 800 nanometer. And the implanted region is roughly, the depth is roughly 90 nanometer. So it's just a thin layer. And 175 keV electron beam comes down. And if we enlarge these parts, the speckled the tunnel structure exists like this, and the speckled region appears in the top layer or surface layer between the free surface and the tunnel structure. It is verified by stereographic observation of the electron micrograph. And further, when we take the picture, this top picture A was taken less than 10 seconds after the electron beam focusing. And the melted region or speckled region appears already here. And after about 60 seconds, it changes gradually. And these black spots appears, and it becomes darker, spotty darker region increases. And then it continues to grow. These are speckled spots continues to grow and stops after maybe after about 2 minutes or so. It doesn't change anymore. And it means that the phenomenon occurs very suddenly. And in this experiment, we could not resolve the time when these speckled region appear. And yes. And the analysis, by analyzing the energy required to melt this speckled region, we have considered two things. First of all, it's energy to raise the surface layer from room temperature to a melting point, and the latent heat of melting. Adding these both quantities, it becomes about 161 MeV per speckled region. It's a very typical or average value, since we have a larger speckled region and smaller speckled region. And the extent of the speckled region from the dimensions, linear dimension of the speckled region, we can calculate the time necessary to propagate the thermal diffusion, to propagate the heat. And it's a very rough estimation, but it becomes about 20 picoseconds. It means that if the reaction continues for a longer time, the speckled region should be spread more. So this is roughly, we consider roughly the duration of the reaction, or it should be less than this, 20 picoseconds. And I'm afraid I have no time already. But all right, I'll mention about the state of the implanted D2 molecules in aluminum. We have done the observation of these tunnel structures, so we can measure its volume. And on the other hand, we observe the contained deuterium by ion beam analysis. We use a method called ELDA, which is a elastic recoil detection method, and we can measure the contained amount of deuterium. And from these two factors, we can obtain the density of deuterium contained in the tunnel structure. And it becomes about 1 times 10 to 22 molecules per square centimeter. Of course, in this case, we neglected the solubility of deuterium in aluminum. It's actually very small, roughly 10 to minus 6 or so. So I think this is not very accurate, but very reasonable value. And yes, so I have to conclude my talk. But we have done some estimations of the chemical reaction and other cause of melting, which are due to the heating effect of 175 keV electron. But we could not. These chemical reactions and heating effects are all quantitatively sufficient to explain the melting, to give the 161 MeV per spectral region. So my conclusion is that surface melting was observed in the deep plus implanted aluminum on 175 keV electron bombardment. The melting was presumed as a result of nuclear reaction because nuclear reaction taking place in the D2 collection, because all other possibilities were deniable. And this nuclear reaction is likely to stop in less than 20 picoseconds. Thank you.
Are there any questions?
When you implanted the hydrogen and the deuterium in the aluminum, did they end up in the same place? Or is it possible that the hydrogen is differently oriented in the aluminum relative to the deuterium?
Yes, we measure the depth of the distribution, and they are almost exactly the same. Its depths are almost exactly the same.
Could you detect any nuclear products like neutrons?
I'm now trying, but I can't say anything about that now. Okay.
Maybe just one more question.
It looked like, I wasn't sure, it looked like you had an X-ray diffraction pattern.
Sorry?
It looked like you had an X-ray diffraction pattern. If you have an X-ray diffraction, was it ordered?
Could you speak more slowly?
I was curious whether the implanted deuterium was an ordered structure. It looked like you had an X-ray diffraction pattern. Am I correct in that?
No, we have done no X-ray.
Oh, you hadn't done?
Not done X-ray diffraction.
Thank you very much. I think we are 5 minutes behind the schedule, so we don't have a collaborator.
Of cold fusion. One is that the deuterium species in the lattice is a deuteron. The second is that the system is subject to positive feedback. And the third is that the system is subject to the laws and deductions of quantum electrodynamics. Now, I think the second one is actually contained. If you ask, Giuliano Preparatus just arrived, so I'll repeat what I said. I said to you, there are 3 things you have to know. One is that the deuterium species in the lattice is a deuteron. The second is that there is positive feedback. And the third is that the system is subject to the laws of quantum electrodynamics. Now, what I was going on to say, Giuliano, is that if you are smart enough, then I'm pretty sure that the second statement, namely that the system is subject to positive feedback, does in fact follow from quantum electrodynamics. But let's just wait and see whether we are smart enough to predict this post facto. But if you don't know it, then you should, then you have to be, I think you have to treat it as a principle in its own right. Now, we've been aware of that, we have thought that there was positive feedback since 1986. Now, have you got some appendix I can point to it? Yes. Now, if we crystallize these thoughts, then we come to the point that, of course, the absorption of hydrogen or deuterium in palladium is exothermic. But if we ask, what will the characteristic be like if we go to very high loadings required to achieve substantial excess entropy production, then we would say that the system is endothermic. And that, of course, has tremendous consequences. Now, we started to talk about this in 1992 in a fairly open way. And the question is, was this just sort of pie in the sky where we're clutching at straws, or is there in fact an evidence when we do the experiment that this is true? Now, our approach, we have really a sort of two-pronged approach to analyzing our data. One is a fairly sophisticated, a rather sophisticated analysis of the behavior of our calorimetric system. But normally, when we try to come to some critical point, we use a very simple analysis, the simplest possible analysis. We have a black box, which represents the calorimeter. We have the electrical energy in, calibration energy in, and we have, of course, heat taken out. In the gas streams, we may or may not have excess heat production, and we have the heat loss to the environment, which in our cells is largely by radiation. And we characterize this by a heat transfer coefficient. So if there is no anomaly in the system, the heat transfer coefficient should be constant. If the cell is such that it would have an invariant heat transfer coefficient. If we do get excess heat production, then the temperature of the cell will be too high, then higher than we would expect, and the heat transfer coefficient will be diminished. On the other hand, if we had an endothermic process in the cell, then the temperature will be lower and the heat transfer coefficient would be increased. So armed with those simple facts, we can look at the data, and I'm very pleased to say that our Japanese colleagues in Sapporo have given us permission to use the results of one of their cells, which is namely cell 4661, which contained palladium silver electrodes. So let me just take you through this and show you how you can recognize positive feedback in these cells. Well, here's the temperature time curve in response to calibration. Here is the cell potential time curve. Observe that if you increase the temperature, the cell potential goes down, so the energy input goes down, so the system is always subject to negative feedback. And as we polarize this thing, this is 600,000, about 6 days along the way, we see the relaxation of the temperature time curve in response to the calibration pulse. We get a quasi-steady state up here. Of course, because the energy input and the temperature time curve are coupled through the negative feedback, we get a fairly fast response. Because negative feedback will always increase the time response of the system. Let's ask ourselves what we see if we go a long way down the line. This is about 2.5 million, 25 days down. We see the same sort of behavior. We again see a fast relaxation. But if we go at an intermediate time, if we don't go that far down the road, if we go at an intermediate time, then we see a very curious feature of the calibration, and that is that we now don't equilibrate. We have a long tail. The temperature continues to increase. So the temperature is increasing in response to the calibration pulse. If the temperature is increasing, the heat output is increasing, and that is positive feedback. So we have both negative feedback and we have positive feedback. And now we see a very curious feature. It doesn't relax back. Normally, I'll show you this in a minute again, it doesn't relax back to the baseline. So we can always spot the presence of positive feedback. This is a very clear signature of the presence of positive feedback. Now, of course, if we wanted to look at if we really want to try and find whether we can see these energetics, the energetics as we drive the thing from exothermicity to endothermicity, we are really looking for a needle in a haystack. So we do need to have a very precise calorimetric system. I say precise. It is not to have an accurate system, because we are just going to go scanning through. Precision is more important than accuracy. And here is something taken from 1992. We have this very simple approach trying to get the heat transfer coefficient. We call it the lower bound heat transfer coefficient because it's the minimum value of the heat transfer coefficient we must have. We see that here the standard deviation is 0.082, relative standard deviation is 0.082%. Here it's 0.11%, overall it's about 0.1%. So we can achieve a precision with the crudest analysis, even not doing any calibration, that of about 0.1%. And here we see we have the application of the heater pulse. This is a platinum blank in D2O, no anomaly. If we do the same experiment with running across, of course, incidentally, the calibrations then are totally normal. If we do the same experiment for an electrode generating excess heat, which is now being driven into this regime of positive feedback, then we do in fact see exactly what we expect to see. As we apply the calibration pulse, the heat transfer coefficient increases, which means there's an endothermic process, a transient endothermic process. If we don't complete if we don't complete the process which is taking place in order to induce positive feedback, then if we cut the calibration pulse, we see a transient exothermic process. So we do in fact see the exothermic endothermic transition. Now, why is this especially important? Well, if you want to get a lot of heat out of the system, then it's obviously better to look at the system after the time at which it has carried out the transition. The second point, of course, which is very important, is it takes a long time to get into that region. And people going back to the early days when people said, well, we'll do an experiment with a palladium. Although we told everybody we have to do an experiment for a long time, people ignored that point, so they never really achieved that condition. But what is really more important than that is that if you can drive the system, if the cause of the positive feedback is this transition from exothermic to endothermic behavior, then of course you are in a conditionally stable condition when you have driven it through that regime, and you can now let the temperature increase, and the charging ratio of the electrode will increase further, and then you have a state of affairs where you can generate heat at an elevated temperature. Because if the system is exothermic, then you would predict that you cannot achieve heat generation at elevated temperatures. So do we in fact see that? So this is the second part, really. Do we in fact see that when we drive the system up to the boiling point? Well, you have to look very, very carefully. We did in fact publish that. This from our published data sets. And if you look carefully along here, you will see that you can see the exothermic, the onset of positive feedback. Let me show you an expansion of that particular overhead, where you can see it much more clearly. Here's an expansion. You see here you have the normal behavior. You have attainment of an of a quasi-steady state. This is the falling baseline here, and suddenly here we get into the region where we apply the heater calibration pulse, and here we see the increase of the temperature with time. It does not recover its original baseline. It's gone into this region of positive feedback. Beyond the region of positive feedback, we allow the temperature to rise, and this is why, of course, we've made the experiment protocol investigation. We allow the temperature to rise. We use a calorimeter where we can condition the temperature time profile. Those of you who are familiar with control engineering will realize, I've talked about this in Maui, that we make the time derivatives of the processes, and Mike was referring to something related to this morning, Mike McCreevy, we make the time derivatives part of the investigation. Okay. So what happens eventually, of course, it increases, the heat output increases, and eventually the cell goes to boiling and it boils dry. Well, let me just, I have a few more minutes, so let me just tell you a little bit more about boiling. It's up on the poster at the back of the hall. Last day, in about 14 hours, the cell boils dry. So how do we set about analyzing these data? Well, again, we like to use, for our first analysis, a very, very simple approach. So we say, okay, the last 14 hours it's going to boil. Let's say there is no excess heat at this point whatsoever. We characterize the heat transfer coefficient, we say no excess heat. Then what can we say about this overall curve here? Well, we can say, suppose there is no excess heat generated. Let's look at the total enthalpy generation. We've just force-fitted the heat transfer coefficient, give no heat at the beginning, and then we get this time dependence of the total excess, the total heat available for evaporation. We have the heat input, the heat output, and the enthalpy, change in the enthalpy content of the calorimeter, and we see that we can't really make that assumption because over the first 7 3/4 hours, the cell is endothermic. Well, we cannot make an endothermic system. We cannot run an electrolytic cell as a refrigerator. That is not possible, not this cell anyway. So this is not permissible, but even if it were permissible, then we only have about 70 kilojoules available to drive the evaporation, but in fact, this will only evaporate about 1.5 moles, just over 1.5 moles of water, but in fact, we are evaporating 5 moles of water from the cell. So the missing 3.5 moles of water have to be removed by the generation of excess enthalpy. We can bring this up in another very simple diagram. Here is this assumption of no excess, that there is no excess enthalpy. We have a shortfall, this shortfall to drive the evaporation. If we allow for excess enthalpy generation, we get this curve. Still not sufficient, and this is why we say that right at the end it's got to go to the boiling point. We can, of course, this should be force-fitting. We can, of course, force-fit the evaporation to ensure that we get smooth evaporation over the course of this last day. And really, it is these two extreme assumptions which allow us to make some statement about the level of excess enthalpy generation during the last day. And we have, this is just really, this is published data. If we force-fit this, if we deny the reality of boiling, then we see we have to go to about 350 watts per cubic centimeter to explain the results. If we say, if we don't make this force fit, if we use the best estimate of the evaporation from the cell, then we get about 20 watts per cubic, 20 to 30 watts per cubic centimeter for most of that day, and at the end it goes up to 4 kilowatts per cubic centimeter. So that is really the analysis of the end result, but the message I want to leave with you is, let me go right back here. The message we would like to leave with you is that if you design the system so that you can look for the presence of the positive feedback, then when you have the system signals you and says, the system has gone through this transition region characterized by positive feedback, if you then let the temperature rise, you will surely achieve high levels of excess heat generation at the boiling point of the electrolyte. Thank you.
Thank you. Do we have questions or comments at this point? Yes, Dr. McCoovey.
If you imagine Baranowski's data to be accurate and make that extrapolation into the endothermic regime, and then estimate the amount of exothermic process that you've seen, the number of moles of palladium that you have, how far have you gone into that endothermic regime?
I don't know that now. This is, I say it is like looking for a needle in a haystack. This is not a terribly easy thing to make the system quantitative. It is very easy to see that you have the transition from negative feedback to net positive feedback. You have to overcome negative feedback. That you can always see. To see the spikes due to endothermicity, exothermicity is pretty critical. My own feeling is that you really want a calorimetry which is still about a factor of 10 better than what we are doing in order to make this into a straightforward technique. But I think it can be done. I think this will probably come in the next year or so.
Other questions or comments? Yes.
How small a system do you think you could see this kind of effect?
Well, those things are done with 2 millimeter diameter electrodes, 1.25 centimeters long. So it's about a foot of a cubic in a relatively large calorimeter. The water equivalent of the calorimeter is 500 joules per Kelvin. And you can see it in that, if you are careful. You could make a system which is more foolproof than that.
Fine. I think this could go on a long time. We have a whole week ahead of us, 4 days, and I propose that we terminate at this moment. Thank you very much. Yes, our next speaker is Dr. Bavarian. The title is Excess Heat Measurement in Aluminum Lanthanum Oxide Doped with Deuterium.
Thank you. So I have only a couple of transparencies, so I can maybe tell you a little story before we get started. A couple of years ago when I called Stanley Pons because I was publishing a newsletter, I wanted to do an interview of him. And he said, what kind of questions do you have? So I said, well, my first question would be, why did you start this work? He said, you know, you're only the third person to ask me this question. I don't remember who were the two first, but I was the third. Anyway, so before starting, I will tell you why we started this work. So let me give you start with the theory first. This is the ideas about the theory. We are using this work has been initiated by Francis Forat. He's now retired from the French Atomic Energy Commission. He didn't do any work himself, but he was working in the past with lanthanum aluminum oxide for laser production 30 years ago. So he was doing some experiments with hydrogen and things like that. So in '89, when the whole thing started, he had this idea of using lanthanum aluminum oxide as a fuel cell, as a cell. So here that it works. This has a perovskite structure. For those who are not familiar with perovskite, I was not 2 years ago. It's not too complicated. It's a cubic system. You have one metal at each corner of the cube and another metal at the center. They are not the same atoms, they are different. So the aluminum is at the center and the lanthanum at the corner, but you can reverse the whole thing. And the oxygens are on the sides of the cube. But you can redraw this slightly differently by putting the lanthanum at the center and the aluminum at the corner. So you have kind of a box. So the lanthanum is surrounded with a number of oxygen atoms. Now we can make this lanthanum aluminum oxide with lanthanum vacancies. You can go up to 5% vacancies of lanthanum. So you end up with a structure where you have a hole. And because lanthanum is trivalent, you could imagine replacing one of these lanthanum ions with 3 deuteriums. So that would just balance charges. Now, if you can put more, you might be able to go to maybe 5 or even more deuterium in one vacancy. So you're close to the density of liquid deuterium, hydrogen, whatever. So this is the basic idea. Now, when you take a sample like that of lanthanum aluminum oxide with lanthanum vacancies, and you put a voltage through the crystal, and you load it with deuterium before, there is 3 zones that will appear. That's called it's nothing to do with the French flag, I think. Blue, white, red electrolysis. But it happens. Some coincidences are not coincidences. In Italy they would have put green, but we don't. Anyway, so in the negative region, the deuterium are attracted by the cathode, and you have an extra density of deuterium in that area. I'll give you the blue color. I have to tell you that this crystal, when it is intrinsic, is white. When it has vacancies, it becomes red due to the vacancies. So I don't have samples with me, but they're just red anyway. So if you load it with deuterium by putting it into the furnace with deuterium in it, it turns out white because the vacancies have been filled with deuterium. So when you put this voltage through the crystal, so you're attracting deuterium on one side and depleting the other zone. So one side we turn back to red, and the other one become blue, and the center, which would be intrinsic, would be white. So that's the red, white, blue, blue, white, red. For the Americans, they'd say red, white, blue. Anyway, that's how you know that someone is French or American. Besides the accent, ask for the flag. Anyway, this is the experimental. Only Americans know that. The experimental setup. We are using a vacuum chamber, which is a 35 millimeter diameter tube. The sample is it's evacuated with a mechanical pump and loaded at atmospheric pressure or around atmospheric pressure with deuterium. One side we have a window to see what's going on, or we'd like to see what's happening, and feed-throughs on the other side. Actually, we have a symmetric system. The sample we're actually using 2 samples squeezed. In the center electrode, we use palladium electrodes. The palladium foil is the cathode, and we have 2 electrodes on the 2 sides of the 2 samples as anodes. The idea of that is to clamp the 2 anodes without making short circuits. So it's much easier in terms of technology. It's hard to clamp positive and negative without some kind of insulation. We have 2 thermocouples to measure temperatures. We are not measuring the temperature of the sample, we measure the temperature of the gas. We have calibrated. Also, we have a third way of measuring temperature, which is slightly odd. We measure the resistivity of the heater. Because the temperature, as everybody knows, resistivity of a wire varies with temperature, linearly with temperature. So we calibrate, we work at constant power. And if there's any heat generated inside the crystal, the resistivity would change. By measuring just simply the voltage across the heater and the current, we can determine the resistivity and therefore the temperature. So we have calibrated this resistor with the thermocouples. And we measure the temperature rise when we put current through the sample. So here now we've been talking about excess heat measurements. So we have also, in addition to the temperature measurement, we have a helium-3 neutron detector. And after that, I don't know if I will ever work with neutrons. I understand a lot of things with neutrons after that. I don't know. No, maybe sometimes you need false signals to keep you going. Because one thing is true, we don't know about cold fusion, but we know we have a good time anyway. So, this is the calibration curve. No, yeah, that's the calibration curve. We put through the sample, this is a lanthanum aluminum oxide emptied of deuterium. There's no deuterium, it's red. The furnace power is 150 watts, and we measure the temperature of the furnace, as I was telling you, by measuring the resistivity. And this is a constant, as you can see it here. At one point, we pass some current through the sample. Current is 1 milliamp, 250 volts through the samples. That is, we put 250 milliwatts in it, and we have a temperature rise of half degree. This is the neutron counts. There's nothing. I mean, no, there's something, but this is just the calibration of the counter. There is a source that creates counts just to make sure things are working. So this is the baseline, and there's no effect. We have half a degree temperature rise that corresponds to 250 milliwatt. All the different curves I'm going to show you have different, same Y scale, but different X scales. The time are not the same, but the temperature scale is the same. See, this is one of the samples. This is lanthanum aluminum oxide with also 0.1% of praseodymium. Don't ask me why there is this thing in it. These samples are 30 years old, and that's all we have, so we just took whatever we had. We put through the sample 0.2 milliamp, and that's about 60 milliwatts, and the temperature rise corresponds to roughly 400 milliwatts. That is an energy amplification 6.5. It's not 6.5%, it's 650%, right? Here we see some slight increase in neutrons. I mean, it's very, very low. I mean, full scale 2.67 counts per second, so forget about it. This is very limited, very, very low. This is another experiment with slightly more energy, amplification of 10, no neutron, kind of very close to zero. Another one here with an amplification of 6, no neutrons. So we only have neutrons once. But maybe it's not neutrons. It looks like neutrons. I mean, if you have neutron detector, you measure something, you believe it's neutron, but maybe it's not neutrons. It could be something else. Noise. Another one with amplification of 6. And another one with amplification of 7. Now, a few things I want to say. I don't know how much left, a few minutes maybe. I can say that. If you compare the rise time it takes for the temperature to rise when we do blanks with just electric heating and with the excess heat, it's different time scale. So there's certainly some effect. It takes some time for the reaction to get started. I mean, in the 20 minutes range, not that much more. This slope is about 20 minutes. Whereas with blank, the time rise is about 5 minutes. So we can see a difference in time scale also. A last thing about neutrons. I had a plan to have more, but now finally I ended up with just in one transparency. That's the one. We have tried to do some neutron experiments doing discharge. What we did at one point where we put some current through a sample, we pumped out the gas, and at our surprise, we saw a huge burst in neutrons. So after fighting for 3 months trying to solve the problem, we realized there was a ground problem. If we plug the counter or some other plug, pulses go away. So now we are very cautious. I read a paper about that last night in the abstract. Someone was warning about neutron measurements, so I got a warning. Now, let me try to conclude. We are sure about the excess heat. We see excess heat at low level of total power. I mean, we're talking about half a watt of energy. People would say, if you have an amplification of 10, why don't you put more current through the sample and get more? It doesn't work. Somehow we're limited in current. It's not proportional to the current. There's saturation. It is very possible that the limitation is due to the fact that it's not a bulk problem. It could be an interface problem. I don't know if it's at the surface, subsurface, inside the cathode, or inside the crystal. Something is happening that's limiting the total output. So I believe we better to have better samples with more surface area so that we can increase the total yield. The problem is that manufacturing these ceramics is not easy. We're working with single crystals that have been grown, as I was telling you, 30 years ago, and we don't have this time machine that takes us back there, so we have to make time, and this time we have to do the same crystals. There is a company in France who is ready to make those kind of samples. So we might, in the near future, have new samples that we can control the vacancies and the impurities that are added to it. So I believe there are a number of parameters that are quite important. The amount of vacancies is very important. I mean, if there's no vacancies, there's no deuterium. But there is a limit of stability of the crystal. If you put too many vacancies, then you will have the crystal will be destroyed. So this is an important factor. We don't know exactly what number of vacancies we have. These crystals have not been manufactured for vacancies. They were manufactured not to have vacancies. So we have very little amount of vacancies in our crystals. Temperature is very important. We work in the 400, 500 temperature range. It seems that if we increase the temperature, it should be better. But if we increase the temperature, and also in our system, we are limited in temperature because of the design of the cells. Also, if we increase the temperature, the diffusion of deuterium inside the sample would change. I mean, if you cannot deuterate these samples at low temperature. You have to go pretty high in temperature. I mean, 600, 700, 800 C in order to have some diffusion of deuterium inside the sample. So we think at higher temperature it will be better. Also, when we put the current through the sample, the effect is that the hydrogen and deuterium is pumped out of the sample. So after a while, if you run the reaction for too long, you will deplete the sample with deuterium and the reaction will stop. So we need to be at a temperature where we have diffusion of deuterium inside the sample and to balance the output of deuterium from recombination. Impurities might be very important, but we don't know yet because we couldn't control them at this point. We have tried quite a few samples. I can show you 4 or 5 curves here, but we have tried quite a few samples, different compositions. Most of the time they work. They're pretty reproducible. It's not that difficult. Current is important, but it has to be low. The electrodes is another parameter we didn't try too much. We tried palladium because we thought it would be the easiest to get started, but we should try some other electrodes too. Surface to volume ratio, certainly to have higher output, we better have more surface to volume. We've used samples that have 3 millimeter thickness by about 2 square millimeter surface, but we might use better systems like ceramics instead of using single crystals. But single crystals are good for basic research. So I think I'm done. So I could find another story maybe to finish my time, make the organizer happy. I'd like to thank Francis Fora for initiating this work and Huntington Laboratories in California for giving me some equipment so I could get started with this work. Well, thank you very much.
Thank you very much. Are there questions or comments?
Your current is very small. Have you tried pulsing the current though and looking at neutrons?
No, we didn't try that.
It would be interesting to try that.
Yeah, you're right.
Another question, yes.
Did you observe and determine somehow the production of heat due to a regular effect of chemosorption, which is characteristic for compounds of lanthanum when absorbing hydrogen? And correspondingly, you can observe the drop of the temperature when releasing the hydrogen or deuterium from the hydrated material.
We didn't do that, but it should be interesting to try with hydrogen. We didn't do any blend with hydrogen, that's right. So we should check that with hydrogen. If we put pure hydrogen, we should see that, if there is any effect due to that.
Good.
I agree.
So you didn't see anything with hydrogen, pure hydrogen?
No, we didn't do the experiment.
Did not do the
We
experiment.
had only deuterium bubbles.
Yeah, Chuck?
A related question, I mean, what was the loading? And did you actually have any hydride formation? You probably didn't.
Hydride inside it. Okay,
I mean, and the loading, do you know what the loading is? I mean, it's quite possible that you could have had stuff diffusing in. For example, from ion band state.
wait.
Well, that's
Let's talk about it at the poster session because I don't.
Well, no, the question was loading. How much loading?
Okay, we load it into, we think it's a few percent. We're not sure.
A few percent loading.
Yeah, it's maximum 5% because after that the crystal is unstable anyway. So it's maximum. Could be but 1%.
Fine. Thank you very much for this interesting talk. The next talk this morning is by Dr. Chelani. The title is Long High Powers versus Pulse Electrolysis, Wire, and Evidence. Thank you.
Thank you very much.
Yeah. Would you put this
Yes,
down in your quote somewhere here? Excellent.
Okay. Okay, morning. This work was made in a new method in order to load deuterium, and mainly to avoid the irreproducibility of the previous experiment. The palladium was given primarily from Imra Material, Japan, some from Tanaka, some Orium, small Italian company. The main motivation is to check if the Cohen effect is coming from Cohen in 30 years was effective in order to increase the hydrogen or deuterium loading in palladium, and moreover to get HST, if any, in a reproducible way. So we want to do technology, not science. Technology need 99.99% of reproducibility. Science is good 1 over 10 million, like high energy physics. We are poor people, we are technology. Okay, to make this experiment, we adopted a quite strange geometry. We use long and thin palladium wires. The geometry is this kind. Only small side of palladium is under electrolysis, and the other is used to check for Cohen effect or other effect, if any. The real schematic of the system is the following. Use this resistor in order to calibrate the system for HST, if any, and some monitor of what is going on. Just to remember some easy formula about palladium. Resistivity is quite low, and to get a voltage drop of 1 volt per centimeter, we need a current density as large as 95,000 ampere per square centimeter. Very big value. And this is the usual formula of electron transport. So to get some useful numbers, we have to get some voltage drop of the order of 1 volt centimeter at least. And there is different diffusion coefficient of hydrogen deuterium changing alpha, beta, or gamma phase. Gamma phase that are from Mengoli group, Padua. And then we used this very big difference in order to get our experiment. There are some interrelated effects. The voltage drop increasing, reducing the diameter of the wire, but it is too small in our experience. It's easy to break. And moreover, the electromigration effect increases exponentially, increasing voltage and drop, but at very large loading, the effective charge of the deuterium decrease, maybe 1/10 of the original value at low loading. A simple way how to operate is this one. So delta voltage has to be as large as possible, so means high current, but to high temperature or a combination of the deuterium and surface, so not a low vapor. We can use another approach. Large voltage means can be used fast rise time. So the effective diameter of the wire is smaller due to skin effect. So we can use large geometry for the wire for mechanical problems and thin for the point of view of the voltage drop. A possible solution can be this one. We adopted the lucky condition of a very big difference about alpha, beta, gamma diffusion coefficients. So we used the method of time variant loading and deloading. So we give for enough long time big power of energy in order to get the loading, and after allow the loading of the system in order to minimize input power. A sketch of the system is the following. For short time we give up to 100 ampere of the wire, means a current of the order 1,000 to 100,000 ampere per square centimeter, very big numbers. And for another very long time we allow the system to deload, but not too much to avoid the full deloading. There is some criteria to follow for pass duration and repetition rate. So the pass duration has to be as short as possible to minimize the input power, but it has to be longer the minimum time in order to get the electrolysis. We found experimentally 300 nanoseconds are enough to get electrolysis. This was a big surprise. But after we can understand, because wind effect helps very much for this kind of experiment. And moreover, the repetition rate has to be as low as possible, but higher than the time between gamma and beta diffusion speed, in order to avoid full deloading of the system. This is our typical operating experiments. We made several experiments. So the longitudinal current density is between 50,000 and 300,000 ampere per square centimeter. The electrolysis current density of the site is typically from 10 up to 100 ampere per square centimeter. Between 10 and 100 times larger than the usual current used. Last time of the order of 100 nanosecond, pass duration real 300 nanosecond, fall time between 100 and 1,000 nanosecond, ignition rate between 5 and 20 kilohertz. We used a different diameter of wire, between 100 and 500 micron and different length, up to 2 meters. Now we are using anode, nickel anode, but we neither use platinum or gold, palladium, and so on. This is the main results we get. Mainly, the time to get loading ratio larger than 0.8 is only 200 seconds. We set this point, only 200 seconds. And after there is other increase up to loading of about 1.1 from simple calculation. For the long side of palladium, the time to get in the bulk 0.8 is 5,000 seconds only, half meter of palladium. And for some side to get some critical point 1.1, only 800 seconds. Moreover, we found that the chest heat, if any, if the calibration is a separate procedure, as a cyclic behavior, and start only after 200 seconds from the beginning. Very, very short time. We studied several wires. The most started was with diameter of 100 micron, 50 centimeter length, and we get at least, in the worst condition, HS energy larger than 60%. Worst condition. Several times we get 150% or more, but the worst condition is 60%. And the output power to order 5 watt, so macroscopic level. Okay, this is the drawing of the resistance changing in the side of the electrolyte. So this side corresponds to 0.6, 0.8, and after this a jump to another value. We understand why this jump, and after decrease again. If we compare these numbers with the effective length of the wire and so on, this value corresponds to about 1.1. So the resistance increase, the loading is from 0.8 up to 1.1, and after come back again to 0.8. So since the system is not strong to keep these big numbers of just heat or something high temperature, and start again to 0.8 in a cyclic way. This point is very important because it's the side of the palladium without a counter electrode, and even the side get intrinsic jump, not related, after 800 seconds. So this is the proof that the electromigration effect is effective. This is the voltage between anode and cathode starting from the zero time. These jumps, this flat correspond to 0.6, 0.8, and so on. Very reproducible. And the mean value corresponds to the bulk effect of loading. So, overall behavior of what we have seen. The point is the decreasing diameter of the wire, increasing length, decreasing rust time, and so on. So all these the main seems the voltage drop along the wire. So the theory of preparator about this point and some preparator communication, do we have the same idea? My experiment, just experimentally, he has a much bigger theoretical approach. And moreover, from the analysis of the short time necessary to get larger loading ratio larger than 0.8 in the long wire, we found experimentally that Cohen effect, even very powerful, is not enough to explain completely this short time for loading. Conclusions is the following. Okay, loading ratio, short time for large loading ratio, short time for HS heat. The HS heat seems cyclically, not continuous. For some short time, there is no HS heat. After start again. Again, the moment of preparator seems fit very well this. So I like this can be a technology, but it's a scientist way. So no technology, no secret, please. You have to be very open if you want to be success. And now, if I can, are very new results. 3 transparency, 1 minute. Okay, in the last time we had a thermocouple between anode and cathode in order to check the real temperature of the palladium wire as close as possible. So we found that the the temperature apparently decrease over time of the thermocouple. So the simple explanation, there is some emission of radio frequency or microwave or something like that, that affect in a big way the thermocouple, the apparent temperature decrease. But this is the temperature of thermometer outside. So it seems that some of the energy is take off because radiation, because some radio frequency, something like that. So at this time, when it's the jump from 1.1 to 0.8, the temperature of a thermocouple seems more reliable. So where this is a minimum of radio frequency emission, maximum of temperature. So this can be a proof that there are another parameter, another effect for loading, for heat transmission. And just to prove again this one, are really new data. So this is after this stabilization time for other experiment. This like energy gain is for hydrogen and deuterium. Please observe this between this side to side. So for hydrogen, all the system is going slowly in some equilibrium condition. The deuterium is fast going, very high frequency of jumps. So what we can see that the hydrogen is slower, and if we take this one like zero of energy, the energy gain is about 60% like before Clement. Just in some more detail, this is the hydrogen behavior, very slowly, is deuterium behavior, very fast in a similar condition. So what we can see, the diffusion coefficient in palladium deuterium system is faster than hydrogen in palladium system. Okay, finish.
Very interesting question.
I would like to make two remarks. I think those floating experiments are very important to understand the mechanism behind the story. Namely, suppose there is some new type molecular states due to some electromagnetic effects like Ramsay suggested a long time ago. Namely, the nuclear spins increase Coulomb attraction between the nuclei. Then you can make two predictions. First, that the volume is going to decrease of the palladium. And two, that you're going to see superconductivity on the surface of the palladium, because the new phase of the hydrogen or deuterium inside the metal behaves for all practical purposes like if you had a solid state hydrogen or deuterium, and then you have Cooper pairs, and you should observe superconductivity on the surface.
Can be, but now in our experimental condition, it will be difficult to check for superconductivity, but in the future, I'll be very happy to do this kind.
Actually, you have the opposite.
No, I have a decreasing of resistance when there is loading.
Yeah, but I mean superconductivity. Otherwise, you wouldn't sustain a potential difference.
Yes, something.
So you have exactly the opposite.
Okay.
I know your major interest was the excess heat, but did you check for neutron pulses?
No, just we check for small gamma emission, but only yes. In the future, we make this experiment in the Kansas laboratory. We have very good neutron detector. Now just for LT pulse, but seems just some strange effect when we switch off the system or when it is loading. So seems like a fractal emission phenomenon, so on. For what I can, yes.
Did you analyze the atomic composition of your reactor before and after the reaction?
Not yet.
Fine. I'm sorry, we have 4 days for further discussions, and would you please, with that, we'll move on to the next talk. Very, very interesting.
Thank you.
Yes. The next presentation is by Dr. Takahashi, Experimental Correlation Between Excess Heat and Nuclear Products.
Thank you, Mr. Chairman. I think the correlation between excess heat and the nuclear product is the key issue of our study, because this is key. Whether we have potential usefulness of so-called cold fusion phenomena or not. So far, we are studying this problem very seriously. And I think everybody can agree with this issue. I see. Okay. I think everybody can agree with this issue that the results of cold fusion experiments since 1989 tell us that the excess heat is not by non-deuteron-deuteron fusion reaction, because of no observation of correspondingly intense neutron, so to say, 2.45 MeV monochromatic neutrons. And therefore, if excess heat or nuclear effect, we should have some new class of nuclear reaction in solids. So far, the many theoretical models have been proposed by many people and drawing very different conclusions on nuclear ashes. However, in my opinion, we can say classify the conclusion on nuclear ash into few scenarios, because we have common factors between different conclusions of different models. And one major scenario I'm drawing is this scenario one. The heat generation is taking place by the emission of high energy charged particles, several MeV probably, by primary reactions. And we have no neutron emissions. However, we have some helium-4 other charged particle generations. And because of high energy of charged particle, we should have some secondary reactions. For example, like neutron emission by d-alpha-n or ddn in the slowing down process of high energy charged particles, emitting high energy neutrons with continuous energy spectrum, probably in 0 to 10 MeV energy region. So, in this sense, it's worthwhile to detect neutron still, especially the neutron spectroscopy is useful, whether we have a continuous energy neutron spectrum or monochromatic. Secondly, I think this is also important because the charged particles in liquid and solids have only very short range, like micrometer, so it's very difficult to detect from outside. Instead, we can detect characteristic X-ray, for example, 22 keV X-ray from palladium by ionization and recombination of K-shell electrons. And also, we may have electron Bremsstrahlung in the recombination process, in slowing down process of high energy charged particles, and emitting continuous energy spectrum, probably less than 50 keV. So we can detect the GSA X-rays instead of charged particles in this scenario. And the second scenario is the production of heat without emitting any high energy charged particles, but producing some transmuted elements like helium-4 and others because of unknown nuclear process. For example, direct energy transfer from nuclear to lattice, as proposed by Professor Schwinger. And in this case, we don't have any neutron emission and no characteristic X-rays. However, we might have soft X-ray emission by nuclear Bremsstrahlung of charged particle slowing down and emitting continuous energy. Thank you. Continuous energy spectrum in this area. And in this case, the emission of high energy charged particle might be the minor branches of this major process. And of course, we can draw some other scenario like this. We have excess heat, yes, but it's not nuclear, but chemical or mechanical process. And however, because of this effect, and this might initiate some very small amount of nuclear process, like flux diffusion and so on. In this case, it may emit this monochromatic neutron, for example. And the fourth scenario is we have no excess heat, but only a few radiation, like neutron and gamma, and with negligible secondary reaction. So we have to pursue neutron spectrum only in this case, or gamma ray spectrum. And the fifth scenario, we have nothing here. This is just the pathological science, something like that. So I think all the results of cold fusion studies will fail in these 5 scenarios, in my opinion. And to do study, experimental correlation between excess heat and nuclear products, we have prepared a kind of comparator of experimental system between foreground run and background run, using a twin system, and making a condition as same as possible for foreground and background devices. And by keeping the electricity current just the same for foreground and background set by series connection. And also the current flow rate and the temperature can be the same by, again, the series connection of flow for foreground and background, and making the same density for electrolyte, and using the same design, open cells and so on. We can make the condition as same as possible between foreground and background. However, only we make I'm sorry. Only difference we made is for cathode material, for foreground line, we use the palladium. For background line, we use nickel. Supposing we have no so-called CF yet for nickel with heavy water electrolysis. I'm sorry. And for nuclear detection system, we have used 2 sets of neutron spectroscopy system using NE213 fast neutron spectrometer, and using 2-dimensional gamma discrimination and measuring the recovery proton spectrum. And for X-ray spectroscopy, we used again the 2 sets of cadmium telluride detector system, again using a 2-dimensional power shape cycle for and also we are monitoring the time variation of neutron and X-ray events by so-called multi-channel scaling system. By doing so, if we have any difference between foreground and background, we can say something meaningful going on. And this is the electrolysis cell. We have a palladium cathode here, it's a plate, and surrounding plasma one is a cooling coil. We have a steroid here. We have 2 sets of these electrolysis cells for foreground and background. And so that's the total system of the experiment. Looks like this. We have an electrolysis cell here, open type. One has a palladium cathode, the other has the nickel cathode. We have NE213 neutron spectrometer here and here, same system, and cadmium telluride here and here for X-ray detection. For radiation detection, we are using the 2-dimensional analyzer, as I said already, and we are doing calorimetry simultaneously for foreground and background and comparing these two things. This is this is a kind of comparator between foreground and background. If you see some detail of the system, we have a cell here, and here is the electrode. We set up the cadmium chloride detector as near as possible because to avoid the accumulation of X-ray from here. Suppose. And we have a neutron detector here surrounding the neutron sheet. And the cell cells. And this is a calibration of cadmium telluride detector, small one. And by using americium-241 calibration source, we can say that we can measure the X-ray with the energy larger than 6 K up to 100 K or so. And this is the property of performance of two-dimensional neutron spectroscopy for pulse height and rise time. So this is a gamma separation. This is a gamma ray contour. This is a neutron contour for the real project cell around. And so we discriminate the signal and take the signal within this area as a neutron. So this is a neutron window. And in the natural background, the gamma ray contour has about 1,000 times larger contour than neutron. So for this kind of separation is really necessary. This is just a calibration for calorimetry. I don't say more about this. And this time I'll show you some results for this kind of experimental procedure using 3 types of palladium sample. I have eye concentrate with this NHE number 1. It's a new hydrogen energy project, so to say benchmark cathode. And this is annealed from the same sample. And we have done the, so to say, low high current mode electrolysis for about 1 month, or 40 days, I'm sorry, and another 10 days for annealed sample. And this is still going on. Let me show very quickly some results. At the beginning of electrolysis, we are comparing the input power and output power for foreground ground. That means a palladium cathode cell. This is a power, this is an X-ray. And here we have some anomalous events coincident with the change of electricity current periodically, 4 times. It's a neutron, just as background layer. And this is happening in the duration of current of period in 30 minutes or so. And having a spectrum like this, it's a continuous spectrum decreasing exponentially in this energy range. And if you compare with the background spectrum, we have no this kind of spectrum. This is for nickel cell. So this looks like in first glance, looks like some electromagnetic noise in our experience, but it might be the nuclear brainstorming. I discuss later if we have time. And the succeeding results after this looks like this. This is foreground, background. This is input and output. We are seeing a little bit difference here, excess. This is for nickel, this is X-ray. We have nothing here. This is just background. We have some burst around here for nickel. And for neutron, only a little bit excess about background, almost background. Something like this. We are taking this kind of data with a particle spectrum. This is the X-ray spectrum corresponding to that kind of burst events. We have this kind of spectrum. And later, we made two-dimensional analysis for this and found this is not X-ray, but some kind of non-X-ray signal, say noise. And for palladium cathode, we have no characteristic X-ray here. So just a background. We have many of such data like this, similar things. And I'll show you some typical. In later time period, we are seeing some excess power coming out like this. This is the output and the input. We are seeing difference, not for X-ray, just a background, and for neutron in the background. So no X-ray and no neutron, but we are seeing excess here for power, excess power generation. And if we extend such, looks like this. This is for foreground. We are showing the excess power here. And this is for palladium, for nickel, for background. It looks like this. So it looks, we might have some excess for nickel, but we are regarding this just as the systematic for calorimetry. And after this, it has become like this. This is for foreground, palladium cell. This is for nickel cell, parallel running. So we are seeing clearly excess power. Only for high current interval. For low current interval, just power zero. For nickel cathode cell, we have almost nothing, just a fluctuation around the power zero. So we can clearly see. I'm sorry. This is tricky. Okay. So by using this kind of excess power data, we are estimating possible error source in the experiment. By using apparent excess power data for nickel cell, we are taking data for many samples and plotted this number of events for individual or being excess power as a function of power balance. And we have this kind of distribution data. And we regard this distribution of, so to say, random and some systematic errors, and fitting this data to the Gaussian normal distribution to have the standard deviation showing the error band of the experiment. This case is 0.65 watt. So we regard this the error band of the experiment. And if we compare this nickel data for power balance distribution and comparing with the foreground data using a palladium cathode, we can see very clear difference between the two. And this is the 3 sigma band. So these events are taking place beyond 3 sigma. So we can say with a 99% confidence level, we have or more, we have excess heat here. However, corresponding radiation, for example, the neutron, we have almost nothing, but we are seeing a tiny, say, structure in neutron spectrum. It's actually bigger proton spectrum, but we are seeing something around here, compared with the background spectrum. Very slight, but we have some. And for the annealed sample, we are doing a similar experiment, but we have not yet obtained a conclusion on annealed sample. But we are seeing similar trend for excess heat. This is for palladium. This is for nickel, just near to the power zero. We have a little bit plus, but less than 3 sigma. Still. Okay. And funny spectrum obtained from the burst event of X-ray from nickel cell. We made this kind of two-dimensional analysis for X-ray spectroscopy. The pulse height was last time. We are seeing the X-ray contour around here. However, we have this kind of contour different from X-ray, and coming from some kind of noise. And this corresponds to pulse height we just observed, as shown here, this component. So we have no X-ray component in low energy, even with the burst events. So the burst events is something different from X-ray events. We don't know what. By summarizing the observed results just in table, in quick view, with this cycle, I want to show we have some meaning for the excess for neutron X-ray or calorimetry. And this cross means nothing. And for X-rays, we have some meaningful data, either for palladium and nickel. And some are proved to be due to some kind of noise signal. And for neutron, we have very slight signal in spectrum, only for palladium, cathode sample. And for calorimetry, we have some positive results for excess heat. However, the correlation between these things and these nuclear products are not very clear at this stage. So I come quickly to the conclusion. In this kind of study, anyway, following the two major scenarios, I set up study of correlation between excess heat and nuclear product is underway. And we have just prepared a kind of comparator for twin system for making a calorimetry neutron spectroscopy and X-ray spectroscopy simultaneously for foreground and background. This kind of system is, I think, a very useful tool for the correlation study from now on. And we have obtained some kind of preliminary data showing the small but clear excess heat. The excess rate is not large, 5 to 7% in this power range, but very clear, beyond 99% confidence level. And observed only for palladium cell. And while no excess heat for nickel cell within this terabyte. And we have not observed any characteristic X-ray from palladium. So we might deny the scenario 1, but still we need a study because we have only one case of data. And however, we have some fictitious burst events related to the mode change of electricity seen for palladium. So we have to study this further. And we have seen a slight increase of neutron in the high energy region, but the correlation with excess heat was not clear. And so far, to conclude the scenarios, I think we need accumulation of many data further for calorimetry and nuclear measurements. Thank you very much.
Are you going to check for tritium?
Yes.
But you haven't yet.
In this experiment, we have not reached an
Not yet. Yes, question.
Do you expect the 22 keV X-rays to come out of your cell with so much of absorbing material?
Yes, yes. Yeah, in our configuration of experiment, we made some trial experiment using the standard X-ray source. And from here to here, we have about 2 magnitude of 2 order of magnitude attenuation. And so we expect still we can detect some.
In your previous excess heat study, you claimed that the neutron emission had gone down as the excess heat had gone greater. Why didn't you expect to see that here? And apparently didn't see that.
I'm not very sure, but probably the amount of excess heat observed this time is not large as the last time. So we could not see the correlation.
Neutrons at all in your studies? Any thermal neutrons? Very low energy neutrons instead of the energy?
That might have, but we have no information because threshold for vector is something like 2 MeV. So if we have a neutron below that, we have no information.
Dr. Chelani?
Maybe the energy of your brainstorm is through and the consideration of few electron volts like nuclear island, non-emission.
Yes, you expect the characteristic X-ray line, but we might have a nuclear brainstorm that emits this kind of X-ray continuously. So far, we might have X-ray from this process for low energy charged particle emission, say less than 100 K.
Yes, question.
Do you check the behavior of your cells with light water as well?
We have not yet checked, but we are planning to do so. Just use a system of light water for background, so we can do so. We'll try it.
These percent gains on the heat are very, very low compared to what you've got before, right? It seemed to me like you had much more spectacular gains.
Yes.
What do you attribute this? Bad palladium from Monaco?
Not very sure. That's a big problem.
While I'm kind of almost starting, I wanted to say thank you for INECO for paying to get me here and for Clean Energy for getting the device here. You may or may not have seen a strange box out there. What it amounted to is we located a strange pig-like creature up on the 3rd floor, and we've got it out here. We're not sure if it's flying or not. How it got to the 3rd floor, we don't know. We want your help to help us determine whether or not it is possible to fly with this thing. It does turn out that flying pigs do have a problem traveling on airplanes, however. More about that in a minute.
You mean this jumbo from London?
Yeah. These Patterson energy cells are different in the cathode design. The cathode is a structured bead system. What it amounts to is you've got a styrene copolymer, which is about almost a millimeter in diameter, 0.8 millimeters in diameter. They then go through a series of processes, but you get a nickel-palladium-nickel surface on the outside of this bead, about 2 microns or so thick. So it's a bead structure which allows us to have a very large surface area. The beads themselves look like this. After the talk, or after the break, or this evening, or all this week, I think, there should be some beads out there for you to examine, to look at. There's also pamphlets and flyers. We have all the manuals for the machines. I think we even may have the National Bureau of Standards certificates for the equipment and whatever you want. I'm not going to be able to go through all my error bars, all the accuracies and statistics in 20 minutes, but that's available. If you ask, we'll try to get that to you. The beads themselves are made first by sorting to a precise size through a sieve system and then hydroselecting, similar to chromatography. They are then sulfonated the outer coating, which makes it charge carrying. They're dipped in copper chloride, which gives it a flash of copper. Then nickel is plated on there, usually by a chemical deposition. For you theoreticians, it may be important to notice that these have boron-containing compounds in our electroplating material. Then it is palladium-coated and nickel-coated. These coats are roughly 2 microns, so they're very thin. This is not my design. This is Dr. Patterson's system, and basically I was called in to put my neck on a chopping block and talk about it here. So here I am. I was busily working with boiling water cells and some things like that, and they tapped me out and said, "Here, you do it. I don't want to get into trouble, so I'll get him in trouble there." This is his cell. As originally I went to his location, saw him and looked at his data. I then went and did the experiment myself. Then I took it back to my location and tried to replicate it. There is now a similar device out here. But in this region is a cell. This piece itself is sitting out on the table. But this is plaster of Paris, which was then used as insulation, which isn't very good insulation, but that's the way it was. The original designs, the thermal efficiencies were around 20 or 30%. So they were throwing away more heat than they were keeping in, which made the calorimetry a little difficult. In a minute, I'll tell you how we did that. This is me at Patterson's location. This is the cell. The cell is in this region. In this case, we stop the water flow with hemostats and stopwatch and measure it that way. Out in the lobby, we've got a flow meter system, which doesn't like to fly very well either. It's kind of, all the data acquisition stuff is not quite up and running. We may bring out the computerization tonight or tomorrow night. While we had it running the way it is, we wanted to let you see it while there's a little bit of a wing sticking out from under the cover, in case it hides again. These are a little cantankerous. The cell itself, this is a little different than in the large poster out there. The beads are in this location, and there is a nylon separator, similar to nylon stocking, but it's a formalized separator. But that means that the gap between the anode and the cathode is very small. The benefits of having a small distance is that you're not losing a lot of joule heating into the bulk of the solution. Most of whatever energy is deposited by the electrolysis is going in near surface rather than through the bulk. I noticed some people's design, I mentioned that in Maui, that the anode-cathode distance, if it's too great, you're losing a lot into just plain joule heating rather than whatever is happening locally. You want most of the energy in that location. If it's too close, it's hard to get a uniform field, but in a heavy water palladium. Originally, these systems that Jim Patterson was working on, and the reason it got my attention is I saw the difference in his light water to heavy water runs. That got me a little bit excited because the calorimetry was not up to the standard that made me believe right away. But the difference between his light water and heavy water runs made me think that there was something there. The run out here is done with light water with lithium sulfate in it as the electrolyte. From the redesign, I put the resistor inside the tube. It was originally outside, which caused for problems in calibration because it was easier to heat the plaster of Paris out here than it was to directly heat the electrolyte. So this tightened up our calorimetry. Also, the one that I use is in a Dewar flask. The device out here isn't the one that the experimental run is done. We did not bring all our bench meters. We've got handheld meters, you know, things like that. So keep that in mind when you look at it. We also glued things down, packed insulation inside. The one out here is probably about 80% or so thermally efficient, 85, 86. The one that some of the runs were done were 96%. And by that I mean the the resistive heating, how much is seen by the water flow. So I moved this inside, insulated it. The original also had metal plates on the top and bottom, which acted somewhat as heat fins, which also complicated the calorimetry. This is now polycarbonate, which helps. The electrolyte flows from the bottom, past the calibration resistor, which you can use during the run if you want, or we've got two leads so that you can run through the resistor and out, or just to the anode, from the cathode to the anode out. There is a metal plate here which is platinum coated nickel. Then there is a platinum screen, then a stack of beads. These beads are 1 millimeter. There's about 1,000, couple of hundred in there. I don't count them, I do it by volume. Then there's a nylon separator, an O-ring, and our anode material is an exchange resin that has been saturated in lithium salt. So that's our anode. Then we have another metal plate with holes in it, well, a screen to keep the beads from falling through, and metal plate with holes to it. Again, that's platinum or palladium coated nickel, platinum in this case. The electrolyte then flows out and you take the exit temperature. So that's the basic cell design. There is one, several actually sitting on the desk out there. And you can look at them. One of them is cracked and all, but it gives you a feel for what the real device was. Once we load this, we put it at constant current around 0.02 amps and run it for several hours. And from the voltage change, we can actually see a drift in the resistance of the cell as the metal surface is hydrating. And it goes, at this range, goes from around 130 ohms up to about 150 ohms, at which time we know that it is more or less charged. The one out here is probably running at 20 to 30 ohms. As you up the current, the resistance drops. There's more charge carrier. So while this is going on, we just sit and wait for a few hours. So I know a few of you were a little frustrated that we had this thing sitting out there and we weren't showing you, but pigs don't like to go up and down elevators, and it takes them a while when you unplug them to get them going again. So you got to sit and wait. This is Jim Patterson waiting for the cell to charge up. And again, the loading time is important. That was about 10 hours. Since we only have about 2 microns or so, the loading times are a lot smaller than you may be used to in a heavy water palladium cell. Just to give you an idea of the units that I'll be using, or the symbols, we have the voltage, the current input, the delta T, the flow of the electrolyte, and the gas flow. And we calculate the power out of the cell into the cell by just the raw voltage and current into it. We don't play the games of minus 1.48. I'll tell you about that in a minute. The heat out is just MC delta T, just raw thermal energy out. A clever person would notice you're not having water through that, so your specific heat isn't exactly 1. It's 0.95. You actually have to calibrate it with each run, and when you're just running it casually, you can circulate the electrolyte and everything's fine. If you're doing extending runs, you actually have to have the reservoir, let it go through, and then collect it at the other end. But you only lose maybe 8 milliliters per amp a day or something like that. So in 200 or 300 milliliters, it doesn't change the concentration too much. The saturated lithium sulfate solution, just to let you know, is somewhere around 3 molar plus, and 100 milliliters contains about 88 milliliters of water. So the specific heat never drops below 0.88. So this number is always between 1 and 0.88. We're running at around 0.95 out here. And in a minute I'll tell you how we play games with the numbers. We're always rounding it to give us the lowest possible number. So when these things come up, we're trying to make it always on the conservative side, so when a critic comes up to us, we can say, thank you for that argument, that raises our heat. We'll get to that in a minute. I think I've anticipated most of those already. The overall system has a reservoir, goes through a constant volume pump, through a filter, 8 microns, through a flow meter to the cell, and then out, and then circulated. The temperature is measured across the cell. Currently it's done by thermocouples across it. We had problems because we were seeing some sort of bias across the thermocouple wells from one end of the cell to the other. We have a common ground on there when we're really running it. And we then didn't believe it, so we went through and put thermistors, which is done by a data acquisition system. Didn't believe that, so we checked the temperature at the reservoir, and as it comes out of the cell, it's not quite as accurate, but it does give you a reality check and make you say, yeah, that is a couple of degrees. You know, do I believe the thermocouples or not? Our flow is normally done with a flow meter. It is a little cantankerous because it doesn't like the lithium ions in there sometimes. But we can check that by stopping this gauge and reading the gas flow, and the old-fashioned way of a stopwatch in the graduated cylinder, turn the stopcock and measure it that way. The important thing to notice is all our measurements have at least 2 backups. Our meters, except for the temperature, can have traceable standards. The voltage and current is taken across the cell. We also have data acquisition, and there's analog meters on the front if you believe it. Analog meters, I don't necessarily believe all the time. Our gas recombination, we do measure the gas flow. It is not very accurate at low current settings because the air comes out as bubbles. So it comes out in bursts as opposed to continuous things. So the meter doesn't like that. At high current readings, it does let us know that we don't have recombination. And by the way, we wouldn't expect it much because we're flowing electrolyte past it, so it doesn't have time to recombine at one of the electrodes, which is usually the site of recombination if it happens. So we know that it's at least lower than 5%. We can't peg it much closer than that because it's an open system and we're flowing. Some of it can be dissolving into our electrolyte and then appearing at the reservoir. So we can't narrow that down much closer than that. But we know that no more than 95% of it is, well, no more than 5 is recombined. Our cell calibration is done across here. We've calibrated through a range. When you look at those charts, realize that you have to account for the 0.95 in your electrolyte specific heat. But this is somewhere around 86% efficient as far as heat, electrical energy in the resistor and thermal energy out. We then calibrate it over a range of input to the cell, and we know that our calibration constant is about the same. The thermal conductivity of the cell doesn't depend on where we put the voltmeter or the volt supply. We've calibrated against the flow rate. The thermal efficiency of the cell doesn't vary much where we put the knob on the water flow meter, what that says. Just before I came in, I took some data. You're welcome to do that during the week to take data and that sort of stuff. This is a typical point. We had 3.8 volts in, 0.12 amps in. I round down on the input, I round up on the input, and I round down on these. Again, being as conservative as I can. I truncate these and round up on these. We're putting in about a half a volt, half a watt. We're getting out 1.7 or so, which is about 3.7 to 1, just raw heat out, raw electrical energy in. If you allow us to make correction of the heat loss, add the 14% that usually leaks out, that boosts it to around 4 to 1. If you allow us to say we don't have recombination that boosts it a little bit more. So all those actually increase the value the way we've done it. The interesting part of it is the last graph, and that is the power versus current. This has a general structure like this, and it appears that in this system, since it's a nickel-palladium-nickel system, at low currents it's more surface area and light water nickel-like. At the high currents it's more palladium-like, and we're getting between 1 and 2 on the high range of currents, and below 0.1 or 0.2 or so we're getting these higher values. It took me a long time to come to grips with believing the low values, and I would advise someone doing this to, before you totally dismiss it, you have to play with it and make sure that your thermocouples are reading and their real values, and know what your error bars and things like that are. But there does seem to be a higher trend down at the low current, and that's similar to what I think was done in Maui by Srinivasan, was that there is a constant excess power that seemed to be related to the surface area on a nickel light water cell, so that you would expect more in this ratio than you would at higher current levels. But it continues on, and all these are above 1, and remember, this is raw heat out. When I actually add the other values, all these points go up if you allow the recombination and the thermal efficiencies of the cells and stuff like that. All that raises the curve. So we do seem to be getting that. Just one more. Raise right there. This is an overlay of the two curves. Of the red ones are without any corrections. The green one, when I add in some of the corrections, it just raises the curve up a little bit. So all the corrections and things we have made so they add to our ratio of power out over power in.
The ordinate is P excess or is it gain?